Hello all, once again I want to welcome you to today's lecture. Today we'll be talking about gas laws. The basic thing we'll be achieving in this class today is to introduce the theoretical concepts in gas laws, and in the next follow-up lecture we'll be solving problems on gas laws. Now immediately let's get it off. Now I have a beautiful quote here. It says, the difference between the impossible and the possible lies in determination. The determination of a man is what separates the possible and the impossible. And I remember a quote in my place. We usually tell people, never say it is impossible. I always tell my students, there's nothing that you can't achieve. Nobody's a barrier between you and yourself. You are the only person that can stop yourself, and no one else can stop you. Let's take it off immediately. Learning objectives. Now, the three things we intend to achieve in this lecture is, number one, we're going to understand the kinetic. Remember earlier we talked about on the first module of this, on the first lecture of this module, we talked about the kinetic theory of matter. In this case, we'll be looking at the kinetic theory of gases because of the peculiarity of gases. Two, we understand how to convert from one pressure or temperature unit to another. Remember, we're going to evoke a little bit of those conversions we did and then practice them a little bit. So we're going to know, because with gases, we'll be talking about gas pressure and temperature a lot. So we're going to understand and review how to do these conversions once again. And finally, we'll understand the mathematical and the theoretical basis of the various gas laws we're going to be looking at. Let's take it off immediately. The kinetic molecular theory of gases. Of course, the first thing that we need to talk about in a gas is the gases are the most energetic form of matter, always moving around in high speed. So let's take it off. We have again about 6 kinetic theory of matter we're going to consider here. So gas particles are always constantly moving through space in different directions and at various speeds. Of course, like I said earlier, before I started talking about this, the gas molecules are the most energetic state of matter. They are free and easily move around in high speed. That is number one. Number two, and that assumption is important because they are the most energetic form of matter. Number two, gas particles have no definite volume. They have no volume, like we said, to assume the volume of the container, and they occupy any space. Of course, they occupy any space they find themselves in. Any space they are in, they occupy it. They occupy any space they are in. 3. Gas particles experience no attractive force. Now, it is assumed that the attractive force, or what we call the cohesive force, the cohesive forces between gas molecule is taken to be 0. So remember these cohesive forces we introduced earlier. The cohesive forces in gas molecules is assumed to be 0, although there are exceptions to this. But at this level of class, we're going to believe that the gas particles have no immediate attraction or accountability to one another because they are just freely moving about without taking into account of their individual molecules. And then the next one, very important, said the average kinetic energy of gas molecule is proportional to temperature in kelvins. This is very correct. That the kinetic energy of gas molecule is proportional to the temperature in Kelvin. This temperature must be in Kelvin Celsius. What that simply means is that as we're going to do the calculations in gas law, we have to convert every temperature, whether in Fahrenheit or in Celsius, we have to convert it to Kelvin for the gas laws to be valid. Now again, molecular collisions, when gas molecules move around, of course, they collide in each other. These collisions is assumed to be elastic. What does that mean? When they collide, they exchange kinetic energies between each other, but the total kinetic energy remains constant. Again, this supports the law of conservation of matter, that no energy is lost, that energy remains conserved. What they simply do is that they collide with one another, transfer these energies, and they don't actually lose it because their collision is highly elastic. What this simply means is that if a gas molecule bounces to another gas molecule, they're going to bounce off completely 100% without having to lose any form of energy. And lastly, when molecules of gases collide with the walls of the container, these collisions is actually what constitute the gaseous pressure. Remember, what is pressure? Pressure simply means the force per unit area. So if they keep colliding with respect to a particular area of the container, that constitutes the gas molecules. And this is exactly the description of the kinetic and the molecular theory of gases. Now, the next thing we need to talk about is we now begin to talk about the gas laws. Gas laws are simple mathematical relationships that describe the behavior of gases. Now, we're going to study gas law by using just 4 parameters of gases. Number 1, we're going to talk about the gaseous pressure. Gases will always exert pressure when they collide with one another with the walls of the container. 2, like we said earlier, gases will always occupy the volume of the container in which they are in. A gas has to exist at a particular temperature, and of course, a gas molecule will have a particular quantity, and that quantity can easily be measured in the amounts or moles of that gas. So these are the 4 parameters that we're going to use in studying gas law. So these 4 parameters will be what will be changed. So simply what all the gas laws does is that to change or manipulate these gas parameters to come up with definite theoretical relationships. So as we're going to see this relationship, we're going to see how this. So the gas laws are going to be looking at here is the Boyles Law, the Charles Law, the Gay-Lussacs Law, the General Gas Law, the RD Gas Law, and the Dalton's Law of partial pressure. Let's take it off from there. But before we do that, we have to understand the pressure of a gas. Now, in gas law calculations, pressure is often expressed in atmospheric pressure. The atmospheric pressure is actually seen to be the standard, the SI unit. It's usually seen as the SI unit of measuring pressure. It's more standard. And the standard atmospheric pressure is simply the pressure needed to support a 750 millimeter column of mercury in a barometer. A barometer is actually an instrument used in measuring pressure. A barometer is an instrument used in measuring pressure. So a barometer itself is an instrument used to measure pressure. So it's an instrument used in measure pressure. Now, and we also will introduce another important unit, torr. The torr unit is simply the pressure needed to support exactly 1 millimeter coulomb of mercury. So what it simply means is that 1 millimeter of mercury is actually equal to 1 torr. And this torr came from an important name. This torr came from the name a man we call Mr. Evangelista Torricelli. Mr. Evangelista Torricelli. I think the right pronunciation is the Italian name is Torricelli. Torricelli was the first person that gave us a very good insight in the use of the barometer. So we call this the Torricelli barometer. How does this work? Now, what Torricelli did in this experiment is to get, this can be seen as a container or a beaker that contains mercury. Then a tube, a long narrow capillary tube is gotten. A long narrow tube is gotten and is also filled with this tube now. The glass tube, is labeled there, so I don't have to write that again. The glass tube is now taken and is filled with mercury itself. Now, this glass tube is quickly inverted into this container that contains mercury again, so that no air escapes into the tube. Now, what we're going to notice here is that this particular mercury, this particular mercury will now begin to empty and fall down, and at a point, it is going to remain level and will stop at this point, which actually this point is actually supported by 760 millimeter of mercury or 29.92 inches. So if you put your meter rule from here, it's going to support exactly 76 centimeter mercury or 760 millimeter mercury or 29.92 inches of mercury. And this becomes the pressure of this point. So what is happening here? What did theoretical tell us? Theoretical now told us that as this mercury, of course, ordinarily you would think that this mercury is going to empty out completely. Why will it remain standing without emptying any further? What happens is that theoretically observe that the atmospheric pressure is acting vertically on the surface of the mercury inside this container. And as this pressure is being applied, it stops the remaining of this mercury inside the tube from being empty. And now when we measure that particular column supported by this length, that becomes what we call the atmospheric pressure. So the atmospheric pressure is actually equivalent to 760 milliliters of mercury, which we actually call 1 atmosphere, or we can say 76 centimeters of mercury. Actually, that is what we call the Torricelli experiment. The Torricelli experiment was widely used in measuring pressure until in 2007, when mercury was declared toxic, and since then it has not been commonly used, and other more efficient barometers that do not have to use mercury has been produced since then. So this is what we call the Torricelli experiment in measurement of pressure. So from this experiment, we found out that 1 atmosphere of pressure is equal to the 760 Torricelli, or 760 millimeter mercury. And this is also equal to 14.7 psi. This means pound per square inches, which is being used in the United States. And this is also equal to 1.01 bar, which is also equal to 101 kilopascal, or is also equal to 29.9 inches mercury. Now, the first problem will be how we convert from one pressure unit to another. That is exactly what we'll be doing now. The question says, the pressure of neon in a compressed tank is 1470 psi. What is the pressure in atmosphere? Remember, the conversion unit has been given to us here. So I'm quickly going back to this to use this conversion unit to do those problems. Let's see. It says, now, what is the pressure in the following? So we're going to convert this into all these units. Okay, let's first of all convert it to atmosphere. If you look at that thing again, 1 atm is equal to 14.7 psi. Let's write that down. You have to always know your conversion factor. That's the first thing you do. 1 atm is equal to 14.7 psi. So going from there, we're going to convert from this to this. What simply means is that we're going to put this on the bottom so that it's going to cancel. So we're going to start. So we're going to say 14.7. No, not 14.7. 1470 psi will be, of course, 1 atm. atm has to be on top. That's what I want to get, over 14.7 psi. And if you cancel this, psi cancels psi, and your answer is going to be 100 atm. That is what we're going to get here. On the second one, we continue working. On the second one, what do we do? It says we're still going to convert this to this. So I'm going to make it in a 3 conversion cycle, just to remind you of the conversions we did earlier. Now we know that there's 1 atm as well is equivalent to 760 torr. If you look at that conversion factor, the conversion factor will always be given to you in exam. Just remember that is this. So now I want to convert it to torr, and I have it in psi. So what I'm simply going to do, look at my scheme. I'm going to take it from psi. I want to convert it first to atm, and from atm I'm now going to convert it to torr. That's what I'm going to do. So it's going to be a 2-step conversion factor. So let me start now. So I'm going to repeat what I did first. So I'm going to start with 1470 psi. First, I'm going to do the first. I want to convert it to 1 atm will give me 14.7 psi. And then if I cancel this first, let's see, I have it in atm. Now I'm going to invoke the second conversion factor. Now what am I going to use? I want it to be in torr, so my torr is going to be on top. So I'm going to say 1 atm will give me 760 torr. And again, if I cancel atm and multiply everything together, I'm going to be getting 7.60 times 10 to the negative 4 torr. Always try to do this math yourself and confirm these answers so that you make sure you get everything. So this is exactly what is going to be given to you. This is the answer you're going to get. And the last one says we should convert it as well to what? Millimeter mercury. You eventually know it's not going to be the same thing. Remember what I told you earlier here, that 1 millimeter mercury is equal to 1 torr. Because what that simply means is that 760 torr is equal to 760 millimeter mercury. So it is the ratio is 1:1. So if we know that and we have it in torr already, you can just say, let me use my red, 1 torr, of course, is equivalent to 1 millimeter mercury. And if that being said, I can invoke that. So what it simply means is that if I have it in this torr, I can easily use my 1 millimeter mercury is equal to my 1 torr. And if I cancel this once again, I'm going to still get exactly the same value, 7.60 times 10 to the power of 4 millimeter mercury. And that is exactly what you get. We go to the next problem, which is also a continuation of this problem we're doing. That is why I gave it 1.2. It says the pressure of neon in a compressed tank is 14.7 psi as usual. What is the pressure in bar? Now, what's the relationship between bar? We just know 1 atm is equivalent to 1.01 bar. And of course, we already know that 1 atm is equal to 14.7 psi. So I want to make it 2 conversion again. Remember again, if you go here, 1 atm is equivalent to 1.01 bar. So I'm going to make it a 2 conversion pack again. I'm going to convert it to atm and then I take it to bar. Let's go. 1470 psi. I want to first of all convert it to atm. So I know that 1 atm will give me 14.7 psi. And then this is, if I cancel this and this now, what I have it to be remaining. Now I want to convert it from atmosphere now to bar, and I know this, I'll use this unit. I want it to be in bar. My bar is going to be on top. 0.01 bar, then 1 atm. And then if I cancel this to this, and I multiply everything together, it's going to give me 101 bar. And now the last but not the least, again, we're going to be converting from this psi, from psi to inches mercury. Of course, we're going to write the conversion factors we have here. So we know that 1 atm again will give us 14.7 psi, and we also know that 1 atm again also gives us, if you go back to that conversion factors, let's see the conversion factor, 29.9 inches mercury. So we're going to get there. So it's going to be 29.9 inches mercury. So we start again. So I'm going to convert 1470 psi. Again, I'm going to convert it to atm. If I convert it to atm, I'm going to have this. And then from atm, I'm going to convert it to what? This. Now I want it to be in inches mercury. So what that simply means, I'm going to say 29.9 inches mercury over 1 atm. And when I cancel out everything, let's say this, we cancel this, and this, we cancel this. And my answer will be 29.90 inches mercury. And this becomes my last answer. So again, I just have to do this a little bit just to remind you of those various conversions we did in the early chapters of this class, particularly in chapter 1. Now, temperature. Again, temperature simply measures the average kinetic energy of gas molecules. That's what it measures. And calculation of gas law is purely done in Kelvin. You cannot negotiate that. If you do it in other units, you're going to lose a lot of points about that, and whatever you did will not be correct. And there's a temperature we call the absolute. The absolute zero temperature is a temperature of 0 degree Kelvin. And at this temperature, it is believed that all molecules have no kinetic energy, and motion actually stops. Motion stops, and no particle will have a kinetic energy or volume at this point. And we use this to actually derive the formula for converting between Celsius temperature to other unit of temperature. So to convert from, remember again, to convert from Celsius to Kelvin, you're going to add the Celsius 273 to the Celsius temperature, and it becomes Kelvin. To convert it back, you have to subtract 273. Remember earlier that we did this thing in the earlier chapter of this class. And now let us begin to look at individual Boyles law. The first law is called the Boyles Law. The Boyles Law describes the pressure and volume relationships of a gas sample at constant temperature. So what that simply means is that we're going to manipulate, basically pressure is inversely proportional to volume. That's exactly how this looks like. So if this is a constant, and when you move this equation and solve it, you're going to have this equation. So what that simply means to you is that at this pressure, that P simply means the pressure of the gas, volume of the container it contains, and K is the experimental constant, and this place, the K actually is a temperature. And if we rewrite this formula, what are we going to get? We're going to get a formula that says that P1 V1 is equal to P2 V2 is equal to P3 V3 to infinity. So remember this, the 1 and 2, ones remain, anytime you see 1 means the initial condition, and the 2's represent the final conditions. So, but at any point in time, we're going to be using just 2 formulas to solve the problem. So at any point in time, the law is trying to say if temperature is kept constant, if you increase the pressure of a gas, the volume is going to do what? Reduce, because the relationship is inversely proportional. The Charles Law. Now, Charles Law describes the temperature and volume relationship of gases at constant pressure. So mathematically, what we simply usually do is that the volume is directly proportional to temperature, so that when you now put a constant of proportionality, you're going to have this. And then when you solve for K, you have this. So at any point in time, V1 over T1 will be equal to V2 over T2. And this is what we call the Charles Law. And the Charles Law itself, the Charles Law itself will always happen at a constant pressure. At a constant. So the pressure is kept constant and the volume and temperature is varied. Again, at any point in time, the 1 just represents the initial condition and 2 represents the final condition. And this experimental constant is actually the pressure at this point in time. The next law, the Gay-Lussacs law. On the other hand, the Gay-Lussacs law is the relationship between pressure and temperature of a gas. It is also called the pressure law or the Monton's law. Now, what simply happens here is that pressure is actually inversely proportional to temperature, which makes sense. As you heat a gas molecule, they acquire kinetic energy and begin to move about. And as they move about themselves immediately, they begin to collide with one another. And remember, we said that the collision of these gases is what results to the pressure of the gas. So the more the collision of these gases, the more the pressure of this gas. And what caused this increase in collision and hence increase in pressure is an increase in the kinetic energy as a result of the increase in temperature. So in this law, increase in pressure will lead to increase, or I just want to say increase in temperature. Increase in temperature will lead to increase in pressure. And of course, at any point in time, P1 over T1 will be equal to P2 over T2. And again, the 1 subscript and 2 subscript represent the initial and the final conditions respectively. And in this one, what is constant? The volume is actually kept constant at this. So the experimental constant here is the volume of the gas. Now, the combined gas law. The combined gas law is just the combination of the 3 laws. Here, so what do? The Boyles Law, we combine the Boyles Law, the Charles, and the Gay-Lussacs law were combined. Gay-Lussacs were combined to come up with this. So if you look at this, so here now the pressure, the volume, and the temperature relationship are mixed together, and they have a particular constant. That constant is what we call the gas constant. However, again, like I said before, the subscript 1 and 2 represent the initial condition, the initial conditions of the gas, and the subscript 2 refers to the final set of the conditions of a gas. And at any point in time, P1 over V1 equal over T1 is equal to P2 V2 over T2. And this is equal to infinity. So if you're going to solve these problems, you're going to at least be given the conditions of these, and one might be missing. So you'll be given a set of conditions missing any one of these variables, and you're going to manipulate this mathematical formula to solve for your unknowns. And we're going to do this example in the next few slides. In the next lecture, I mean to say, the ideal gas law. The ideal gas law relates, in this case now, remember, in all this gas law, we said there are 3 parameters we need to talk about: the pressure, the temperature, the volume, which has been addressed in the 4 previous laws we talked about. Now, the ideal gas law is now the one that has the relationship between the 4 of them. So in this law, the relationship between the pressure of a gas, the volume of a gas, the temperature of a gas, and the number of moles of gas are brought together in what we call the ideal gas law. However, a constant which we call the universal gas constant comes in, and the value of that gas constant is 0.0821 liters atmosphere per mole per Kelvin. So this is what we call the ideal gas laws. And this constant will always be given to you. And for you to apply this particular formula in doing gas problems, your unit of volume must be in liter, your unit of pressure must be in atmosphere. You have to convert, if you have the mass, you have to convert it to the moles, and the unit of your temperature must be in kelvins if this formula is going to be used for you to work. There could be, this formula can be manipulated to other units, but at the level of this class, we're going to be sticking to this particular unit and this particular value for our gas constant. And lastly, the last but not the least we're going to be considering is the Dalton's law of partial pressure. Now, the Dalton's law of partial pressure is a law that states that the total value of the pressure of a gas, of gases, which do not interact chemically, is equivalent to the sum of the individual gas pressures of those gases. So the pressure exerted by a mixture of gases that do not react chemically is equal to the sum of the partial pressure of those gases. A partial pressure simply means the pressure of an individual gas. That's why we call it partial pressure. The pressure of an individual gas, if it is contained alone in a container. Mathematically, PT means the total pressure. This means the total pressure. Whereas, well, that pressure doesn't seem to be clear as I want it. Okay. Whereas PA, PB, and PC represent the individual gas pressure for other molecules. So now, so if you wanna, let me try to represent that. The law is trying to say that if you have a mixture of gases, let's say you have a mixture of gas A. So if this is, let me say this is gas A. The circle is too small. Okay, this is pressure of gas A. If this is gas A alone, gas A alone has a partial pressure of PA. Gas B will now have a partial pressure of, so this is gas B. What it means, if you measure the pressure using a pressure gauge, it's going to give you PB. Okay, it's PB. And then plus, again, this is going to give you PC if you use a pressure gauge on this. Now, what is trying to say that all these 3 gases have their individual pressures, and the pressures are PA for gas A, PB for gas B, and PC for gas C are their individual gas pressures. However, if you want to know, if you mix all these 3 gases together and you want to know their total pressure, it's trying to say that the total pressure is going to be, of course, if you mix all of them together, you're going to have more pressure, which is going to be, this becomes A plus B plus C. That the total pressure is now going to be, okay, I'm going to make that in better. That the total pressure is now going to be, of course, this is going to be your P total is going to be, oh no, I need to make this is my animation. I need to make it very clear and beautiful. So the total gauge is going to be, P total is going to be PA plus PB plus PC. And this is what we call the Dalton's law of partial pressure that states that the total pressure of a gaseous mixture which do not interact chemically is equal to the addition of the partial pressure of those gas molecules. And at this point in time, thank you for listening. And in the next lecture, we're going to be talking about gas laws problems. Thank you for listening and do have a wonderful day.